Today we are starting our unit on astronomy, and we're starting with some basic information about how the Earth moves in space. So the Earth moves in space in two major ways. First way is revolution. Revolution is the movement of one object around another object. What object does the Earth revolve around? Well, the sun. Okay, so you have see in this picture here, the Earth is revolving around something, okay, and the sun would be over here. How long does it take the Earth to make one revolution around the sun? It takes 365 days. Well, not exactly 365 days, more like 365.24. Or really, it's 365.242199. Okay, that's how we have a leap year every 4 years, because it's not exactly 365 days. It's a little bit longer. So every 4 years, we add February 29th in to get that a little bit closer. But now by adding February 29th, it makes it 365.25. And that's not right. Okay, that's not exactly right. And that can be a problem. So let me tell you a little bit of a story here about this. And I'll make it quick because this lesson is fairly short. Leap year goes back from a guy named Julius Caesar. There you see him. And in 45 BC, he revised the Roman calendar, which was based on the lunar cycle, to have 7 months of 30 days and 5 months of 31 days. Okay, that made 365 days. Every fourth year, he made a leap year. Okay, that made the Julian calendar 365 and a quarter days long. Okay, and again, not quite right. Well, Julius Caesar was a great ruler, and then Caesar Augustus came along. There he is, and he was a great ruler also. So after he died, the Roman Senate renamed the months of July and August to honor them. Okay, so July is for Julius and August is for Augustus Caesar. They also made July and August 31 days long because they were such great rulers, they needed to have months that had the most number of days in them. They realized that they couldn't just add days to the year, so they took those days away from a month. And of course, that month was February. So February went down to 28 days instead of being at 30 days like it had been. And then, of course, the 29th day is when the leap year, they add that into February. Well, so if we have 365.25, you'd think that'd be close enough, but really it's not. That Julian year is actually still 11 minutes short because of this number. Okay, it's not 0.25, so that means each year is 11 minutes short. So over time, that adds up. Okay, 3 days every 400 years. So that by the time Pope Gregory XIII came along, there's Pope Gregory XIII, the seasons weren't happening at the correct times. Okay, so basically Easter wasn't happening when Easter should be anymore because it gets off 3 days every 400 years. So to get the seasons correct, what he decreed was the day after October 4th, 1582, would become October 15th. So all those days, so 11 days in history there, were just skipped. Okay, Pope Gregory just skipped those 11 days from October 4th to October 15th. So imagine if you had a birthday then or were paying rent for that month. So a lot of people weren't happy with it, but it didn't matter. He was the Pope, so he decreed that the day after October 4th was October 15th, and so it was. Then to keep that basically so it wouldn't happen ever again, he came up with these other rules. And I'm just going to kind of go through them really quickly. You are not going to have to know these for certain. So the first one we know, every year divisible by 4 is a leap year. Okay, we have February 29th. The next, every year divisible by 400 will not be a leap year, even though it should have been a leap year. Okay, so we'll go 8 years without having a leap year then. Next rule, every year divisible by 4,000 will be a leap year, even though it shouldn't have been a leap year by the 400 rule, but should have been a leap year by the every 4-year rule. And if that wasn't confusing enough, then we have the every 20,000 years will not be a leap year when it should have been a leap year, but then shouldn't have been a leap year, but should have been a leap year. Okay, so it gets kind of confusing, but basically divisible by these 4s. Okay, so that's the first way it moves. Revolution, the Earth goes around the sun. The Earth also spins on its axis. That's called rotation. Okay, so rotation is the spinning of the Earth on its axis. How long does it take the Earth to rotate? Okay, you should know this, right? 24 hours. Now, Is it exactly 24 hours? Of course not. It's a little bit less than 24 hours. So do we ever have to correct that? Yes, we do. So occasionally, basically at midnight of December 31st going into January 1st of the next year, sometimes we'll add fractions of a second to correct the day to make sure that we all stay on track. Okay, but anyways, we're moving, Earth moving in space, revolution going around the sun, rotation spinning on its axis. Okay, why do planets revolve around the sun? We really already learned this during our physics units. Okay? We see the two main forces. Gravity attracts objects toward each other. So basically gravity is trying to pull the Earth towards the sun, okay, a fiery death. But inertia, the second part, an object in motion continues in a straight motion in a straight line. So inertia says we're going to go in a straight line and the Earth is going to go out and freeze to death. So what happens? We go in between them. Okay, they balance. So we go over here, now the Earth is over here, let's say. Gravity says, die of fire death. Inertia says, nope, go out in a straight line, freeze to death. So what we end up taking is this curved path around the sun. Okay? This curved path of revolution is called an orbit. Okay? So revolution, orbit, they're very similar, but there is a little bit of difference. Revolution is the act of going around something. Orbit is the path something takes as it goes around. Okay, so revolution is going around. Orbit is the path it takes as it goes around. Okay, it's very simple, just a slight difference. Okay, so orbital motion, let's talk about the orbit a little bit. The orbits of the planets and moons are never perfect circles. They're always slightly eccentric, okay, a little bit out of oval. And you might know this word eccentric. Okay, maybe you describe a person. Maybe you describe a person as being eccentric. They're a little bit out of round, or they're a little bit oval, okay, a little bit different. Okay, and that's what eccentric means. It's not a perfect circle. Johannes Kepler came up with 3 laws of planetary motions, and his first law is about the shape of the orbit. We're not going to go into the laws, we don't have time for that, but if you look them up, you'll see that the first law describes the shape of the orbit, and it is always going to be oval. It's always going to be eccentric. And you see the Earth going around the sun. Okay. Now the Earth's orbit is not that oval, of course. We're fairly close to round, but we're a little bit off. So as we're going around the sun, if we're oval shape, that means at one point in our orbit, we're going to be close to the sun. Okay, closer to the sun than another point in the orbit. Okay, the point in the Earth's orbit when we are closest to the sun is called the perihelion. Okay, so perihelion is when we're closest to the sun. In this case, it would be there. Okay, helios is sun, so perihelion is close to the sun. Aphelion is the point in the Earth's orbit when we're farthest from the sun. So that would be here. Okay, aphelion's farthest from the sun. Easy way I used to remember it is the A here. A away, okay? A away. Aphelion means we're furthest away from the sun. Think of the words perigee and apogee. Okay, what do you think they mean? It's going to be closest to something and farthest from something. What about the G, do you think? Okay, that's for the moon. Okay, so perigee is when the moon is closest to the Earth, or we're closest to it, and apogee is when we're farthest from the moon, because the moon goes around us in an oval also. So now we look at a picture like this, and we see, okay, we are farthest from the Earth on July 4th. Okay, 152 million kilometers. We're closest to the Earth on January 3rd, 147 million kilometers. Okay. So is the distance to the sun the reason for the seasons? No, certainly not. Okay, we're closest to the sun when it's cold outside. We're farthest from the sun when it's hot outside. Okay, so there's a different reason for the seasons. And the reason is actually the tilt of the Earth. Okay, we have summer when we're tilted, so here's the Earth. We're going to go over this later, but our axis is tilted towards the sun, making it summer. Okay, when we're over here, our axis is tilted away, so we're getting less hours of sunlight. So it works out perfectly for us in the northern hemisphere that during our summer, we're farthest from the sun, so our summers aren't as hot as maybe they might be. And then our winters, we're closest to the sun, so our winters maybe aren't as cold as they could have been. So it works out nicely for us. So just realize, again, that the seasons are not caused by the distance to the sun. It's actually kind of opposite. Okay, and we'll talk about the seasons in the next lesson. Oh, and this shows the apogee. Okay, so the distance from the moon far away to close. Then the last thing I just wanted to show you here were time zones, and you see all these world time zones map. And this deals with the Earth rotating as we revolve. Okay, and the goal of time zones is to have it when it's noon, have the sun overhead. Okay, so that's why we have these time zones. If we just had one big time zone, then whenever it was noon, wherever we picked, maybe in London, okay, since we have a 6-hour difference to London, essentially, when it was noon, it'd be only 6 o'clock in the morning for us, or the sunlight would be like that. Okay, so what we try to do is get noon to be overhead for us. And you see kind of interesting things with the map, maybe like China is all one time zone. Okay, there are no separate time zones in China. Their time zone is what Beijing is under, okay, the capital. So it can be kind of interesting. Morning over here in the far western edge is really dark. It doesn't get light for hours because of where in the time zone they're in. You also see the international date line. That's a 24-hour time difference. And we can talk more about this in class if you want to know more about time zones. But that's it for movements of the Earth. Basically, it's that revolution rotation idea, going around the sun, revolving, following an orbit, and then rotating on the axis.